Hi, so this is my Lab 3 circuits report. So, introduction to circuits. The main purpose of this lab was to use what we had learned about parallel and series circuits in class and test different possibilities, like test how different orientations of a circuit could affect things like voltage, current, based on factors such as resistors and capacitors. Our system was a circuit, and our surroundings was just the surroundings, but didn't really have any, didn't matter in this context. So some physics principles that are important to note here is that we needed to understand what potential difference was, which is just change in voltage. We needed to understand Ohm's law, which is the relationship between current, voltage, and resistance. And we need to know node and loop rules in order to create equations that would help solve for these different parts here, such as current, voltage, and resistance. Problem 1, we had a series circuit with 2 ammeters and 2 resistors. I would like to note here that this we had to work with one battery because our other battery was not working for our table, so your numbers may look slightly different than ours. So when the first circuits we made, we had to predict the voltage, the current, so we knew the voltage of the battery, and we knew if we just added up the total resistors, we would get the resistance. And so that was what we got as our current, and the actual reading was incredibly close to that. So if we reverse from the connections to the ammeters, we realize that it changes the sign, but it's the same magnitude. So then we decided to connect a voltmeter in place of one of the ammeters. Now, a voltmeter in general has a higher resistance than an ammeter, which is going to be important to note later. And we noted that it was around 1.5 volts on the voltmeter and 0 amperes on the ammeter for the current. Then we had to find the potential difference across each component of the circuit. So in order to do this, we had to take into account loop rule, which told us that this voltage of the battery had to be used across this resistor and this resistor. We could ignore the ammeter because we assume for this that it has 0 resistance, so it is mainly between these two here. So all we had to do is we would then, so we know the voltage of the battery, and then we also know V is equal to I times R. So then we just plug that in. We already know the current because we got from the last slide, and hence we got our numbers. And note again, this and this number do add up to 1.5, and we found the actual readings were also incredibly similar. So this is a physical representation of the potential differences we calculated just previously. As you can note, we start at 1.5 volts here, we come across a resistor, so it slightly goes down. It once again plateaus here, and then it goes down with the resistor, and that's why we get 0 around the ammeter. The ammeter doesn't change reading because it's a resistance, so it stays the same. It doesn't really have an effect here. So we worked on a parallel circuit next, where we essentially took a voltmeter, put it in parallel with the 100 ohm resistor, and so this ammeter's still here. So what happened to the current going through the other ammeter? So the ammeter now has a lower resistance, so the current flows through the ammeter, and it creates an increased reading for the ammeter rather than going through the voltmeter first. So resistance of each element using, again, Ohm's law, resistance equals voltage divided by current. We found resistance of each piece. We took our actual measured values. And as you can see, these numbers are incredibly similar to what we have here. The wires have none in them, and the ammeter also, we agreed, is negligible. So then we had to look at an RC circuit. An RC circuit stands for a resistor-capacitor circuit. We tested 2 light bulbs on this circuit. We had a 10 ohm and a 20 ohm. The 10 ohm obviously took less time to reach the capacitor because it's not creating as much of a resistance to the current and voltage that's trying to come around. So obviously those numbers make sense there. And then we had to essentially analyze, we were given a new problem here where we had to analyze the RC of the circuit. So when calculated, we essentially can take the resistor times F, and then we get what the RC is of that circuit. But then we could also use this equation and then manually plot in some of our numbers that we had, and the graph RC is just 1 over slope, and that's around 4.44 seconds. So understanding the possible problems we might have had, we could have had some faulty equipment. Our recorded values of the ammeter voltmeters could have been slightly off because of faulty equipment. We also assume the ammeter has no resistance, but it could have a little bit in reality, right? And we also assume that the battery was at full voltage when it had been used prior to our lab, so that could have also been an issue here. So some what ifs, if we had charged a capacitor with no resistor in the circuit, the RC would be 0 because there is no resistance to plug into our equation. So again, 0 times any number will be 0. So if we have no resistor, the capacitor would immediately discharge and charge. But in real scenario, there's always some resistant, like wires. If we were to charge the capacitor directly through a battery and measure the charge and discharge over time, we would find we are in an incredibly similar scenario once more, like this one up here, where essentially no resistance means immediate discharge and charge, but in reality there will always be some sort of resistance. Overall, our physical model made in class was extremely accurate, and we were able to demonstrate our knowledge about circuits and understand what we built. Thank you.